Hello, this is a list of nodes which we are going to discover in this lesson. These nodes are very basic and you will use them almost all the time, so we'll start directly with them. Okay, let's get started. Now we need some geometry. Double-click and dive inside. Let's choose a polygon, then put a frequency to 30. Now let's type a VOP. As you can see, there are many geometry VOP nodes, such as point VOP, primitive VOP and vertex VOP. These three nodes are just presets of one single attribute VOP, the only difference is the geometric attribute class is already assigned. So I'm going to use the attribute VOP almost everywhere. Select the class of geometry attributes, which we are going to modify. Then plug the geometry to the first input and dive inside. Inside VOP context, you will find these two nodes. The big one provides outputs that represent all the global variables for the attribute VOP network types. The small one is a simple placeholder to write out common attributes from attribute VOPs network types. Now let's create an add node. This operator outputs the sum of its inputs. Connect P to the add node. P is a position of each point. Now let's connect sum to the output P. As you can see, nothing has changed because we still don't add anything to the position vector. Now let's create a constant node. This operator outputs a constant value of any vex data type. The constant node by default creates a float value. Let's specify it as a 3-float vector. Okay, let's add this vector to position. Look, now we can move the sphere as we like by changing this vector. There is a more efficient way to create constant node. Let's delete this one, then right-click over the second input and choose a constant. Houdini automatically creates for you the constant node. Just specify the type. Okay, let's delete it again. Now I want to continuously move the sphere upward during animation. For that, let's create a float to vector node. This operator converts 3 floating point values to a vector value. These 3 values can be used to represent positions, directions, normals or colors. Plug the output vector to the second input. Then plug the time to the y component just to move along the y-axis. The time is a global time at which the volume is being evaluated. Now let's run the animation and see what we get. The sphere moves up because the time drives y component of the vector. Plug to the x component to move the sphere in x direction or along to z direction. To increase the speed, we can multiply the time by a value greater than 1. Let's create a multiply node. This operator outputs the product of its inputs. Connect it to the time. Now let's create a constant node and multiply by 5. As you can see, the sphere moves 5 times faster. To slow down, you must multiply by value less than 1. Now the sphere moves 10 times slower because we have multiplied by 0.1. Another way to slow down motion is to simply divide the time by a value greater than 1. Let's delete these two nodes and create a divide node. This operator outputs the result of dividing each input value by the next. Let's create a constant value and divide by it. Now the sphere moves 5 times slower because we divide the time by 5. There is a more convenient form of multiplication or division for this type of simple math operations. Let's delete these two nodes and instead create a multiply constant node. The multiply constant node represents a simpler version of the multiply operator because it does not require a second input. It is ideal for scaling a value by a constant. The same applies for the divide node and called divide constant. Okay, let's delete it. In case if you want to reverse the direction, you have to multiply by negative value. There is also a separate node for such a simple operation, which is called negate. Let's create it. This operator negates the incoming value. It simply represents a simple version of multiply constant node, which performs a multiplication by -1. Now let's do the same thing in a different way while learning a few other nodes. First, let's delete all these nodes. Then create the vector to float node. This operator unpacks a vector into its three components. Actually, this is the opposite action that does the float to vector node. Now let's wire up a position. Then create a float to vector node and connect accordingly all these vector components. And of course output vector to P. Nothing has happened so far because the position vector has not subjected any change. Let's create an add node. Then connect the y component of the position vector to it. Look, the y component goes through an add node. This means we can add any value to it. In our case, it will be time. Now let's run the animation and see what we get. Here we go, we have the same result but implemented slightly a different way. Let's change the direction along x-axis. For that we only need to connect x component instead of y. That's it, the sphere moves along the x-axis. I also want to introduce you the subtract node. Let's create it. This operator outputs the result of subtracting all its inputs. It means after subtraction the sphere will move in the opposite direction instead of adding. This is simple math, I just want to introduce you to subtract node. Here we go, the sphere moves in the opposite direction. There are also simple forms of these two nodes, called add constant and subtract constant, which do not require a second input, it's already built into it. Okay, I also want to introduce you two more nodes. Let's create the first of them, which is called a set vector component. This operator assigns a value to one of the vector's components. In this situation it can completely replace the float to vector node because we modify only one component of the vector. Now let's create the second one, which is called the get vector component. This operator extracts a vector component. In this case the get vector component can completely replace the vector to float because we need to extract only one component of the vector. Okay, let's connect a position to it. Then specify which component to extract. We will select the component 2, which is the y component. Then plug it to the first input. Let's also get rid of these two nodes. Connect the difference to the vector component, which needs to be changed. Give it a position vector. The modified position goes to the output P. As you noticed, something strange happened with the sphere because we forgot to select the y component. Here we go, now we have the same result. Let's also reverse the direction simply by adding the negate node. To change the axis along which the sphere moves, you just need to change the vector component of these two nodes. That's it, the sphere moves along the x because we select the first component. Now let's do something more interesting based on this concept. First let's delete all these, we no longer need them. Let's type a noise and choose a turbulent noise. This operator can compute three types of 1D and 3D noise based on point position. Let's also create an add node because we are going to add a noise to the position. Connect a position to it. Look, the noise output float value because by default is selected 1D noise. Let's select 3D noise. I also want to change the type of noise. Select the original Perlin noise. Now we can add the noise to the position. Look, the sphere has been deformed. Let's adjust the noise settings. Look, sliding the offset moves the noise. Now I propose to drive the offset by the time. We have already done something similar. Let's create a float to vector. Connect the output vector to the offset. Then connect the time to the Y component. Now let's run the animation. Here we go, the noise moves along the Y-axis. We can also replace the float to vector node by set vector component, which we already know. Connect time to vector component and the output vector to the offset. Delete this one. Now let's select the second component of the vector and run the animation. Nothing has changed, the result is the same. Okay, that's all for this lesson. In the next lesson we are going to discover the big list of new useful nodes, as well as already familiar nodes, but in other circumstances. See you in the next lesson. Hello, this is a list of nodes which we are going to discover along this lesson, and also we will use the nodes that we already studied in the previous lesson. These nodes are also very basic and they will often be useful to you. Okay, now let's create an empty geo node and jump into it. Then create a line and change the line direction along X. Put a 10 for line length and 200 for points. If points are not displayed on your viewport, just click on this. Okay, let's drop down the attribute VOP. Connect to it the geometry. Then dive inside. The first thing we need is a getVectorComponent node, let's drop it down. Connect position. Then select the first component. This means we have extracted only the X component of this vector. Let's also create a setVectorComponent. Connect position. Then connect the extracted X component to here. And select the second component. This simple setup means that we drive the Y position with the X position. Well, let's connect the edited position to the output P. Here we go, we get a linearly growing line. Instead of linear growth we can do something more interesting. Let's create a sine function. This operator performs a sine function. The input has to be radians. As you can see, the curve is deformed as a sinusoid. In order to change the frequency of sine, you have to multiply some value before sine node. Let's create a multiply constant node. Look, changing the multiplier the frequency changes. To offset the sine, we just need to add some value before sine node, let's create an add constant. Take a look, the sine is shifting. These two nodes can be replaced with one single node. Let's remove them first, then create a multiply add constant instead. This operator will take the input value, add the pre-add amount, multiply by the constant multiplier, then add the post-add amount. As you can see, with this node, we can control both frequency and offset. We can even replace these two nodes with one node. Let's delete these two nodes and create a trigonometric functions instead. This operator performs a variety of trigonometric functions. The argument must be expressed in radians. Take a look, the frequency and the offset are already built in it. You can also change the function type. Here you can find all trigonometric functions. Of course, they also exist as a separate nodes. Now I will show you a few of them. Here they are, cosine and tangent as separate nodes. Okay, let's get rid of them. In case if you want to change the amplitude of the sine, you will need to add the multiplier after the function. Let's create a multiply constant and connect before the function. Look, changing the multiplier changes the sign amplitude. Okay, let's go on. Now I want to introduce you to the clamp node. This operator clamps the input data between the minimum and maximum values. Since the default minimum value is 0, values below it become 0. Look, changing the min value we change the minimum allowable value, and changing the max value we change the maximum allowable value. Okay, let's delete the clamp, we don't need it anymore. Now I want to introduce you to another useful node, which is called absolute. This operator computes the absolute value of the argument. It can be used to convert negative values into their positive equivalent. As you can see, all negative values became positive. Let's turn this off and on, just to see the difference. To change direction along the negative y-axis, we can simply add a negate node. Okay, let's delete it too. Now I propose to complicate the setup a little. Create a fit range node. This operator takes the value in the source range and shifts it to the corresponding value in the destination range. Values outside the input range will be clamped to the input range. Let's connect to it the position along x. Look, in this case the source min is 0 and the source max is 10, so here we have to set 10. The destination min and the destination max we will leave as it is. In simple words, we took a range from 0 to 10 and squeezed it from 0 to 1. Now let's create a multiply node, then multiply sign amplitude by the destination range from 0 to 1. That's it, the amplitude grows linearly. To invert a linearly increasing amplitude, we can just swap the maximum and minimum. Let's temporarily make the destination range from 0 to 2. Now I want to change the linear growth and make it exponential. For that, let's create a power node. This operator raises the first argument to the power of the second argument. Here we go, we can control the sharpness of exponential growth. In this case, the maximum value increases because the range from 0 to 2. If we make the range from 0 to 1, the maximum value will not increase. Okay, now let's delete the power node and create a ramp parameter node. The ramp parameter node represents a ramp user interface. As you can see, the output of the ramp is a vector because by default the ramp type is set as a color ramp. Let's choose the spline ramp. Look, the output becomes a float. Okay, now let's give an input range to the ramp. Then multiply the amplitude by the ramp output. As you can see, the sine wave is gone because the spline ramp is 0 by default. The spline is promoted at the object level. Here it is. Let's tweak it and see what we get. As you can see, the spline controls the sine amplitude. Let's get back inside the VOP again. Now I am going to plug the output of the spline ramp directly here by passing through the sine deformation. We can also get rid of all these nodes, we don't need them anymore. Let's arrange the nodes to make the network more readable. Then jump to the object level and see what we get. As you can see, the line now follows the exact shape of this spline. Okay, let's jump inside again. Now I propose to create a spiral. In fact, all those nodes that we need to build a spiral we are already familiar. First, let's delete all these nodes except the getVector component, then create a float to vector node. Plug the output vector to P. Connect the extracted X component to the corresponding X input. Now let's create a sine function. Plug the extracted X to the sine input. Connect the output to the Y component. Now let's create a cosine function. Plug it to the Z component and give an input. Here we go, the spiral is ready. Finally, let's make the frequency and offset control by adding multiply add constant node before sine and cosine function. Here we go, now we can control both. Okay, that's all for this lesson. In the next lesson we are going to discover again a lot of new nodes. Hello, this is a list of nodes which we are going to discover along this lesson, as well as we will use the nodes that we already know from the last 2 lessons. Okay, let's get started. This time we will use a torus. Let's jump into it. Put a 300 for rows. 600 for columns. Let's drop down the attribute VOP. Connect the torus. And jump inside. Let's expand the workspace. We can minimize this shelf to expand the workspace even more. Let's also minimize the timeline. Now let's create a displace along a normal node. This operator displaced the surface along the surface normal by a given amount. Plug the displace position to output P. Look, by changing the displacement amount, the geometry is displaced along its normals. Now I propose to drive the displacement amount by the noise. For that, let's drop down the turbulent noise. Connect position to it, then connect 1D output to the amount. Look, the torus has displaced by given noise. We can also scale the displacement amount. This is a simple multiplier, that's why the negative values invert the displacement direction. I also want to change the noise type. Select the original Perlin noise. Then adjust the noise settings. Okay, it's good for me. Now I want to introduce you to the maximum and the minimum operators. First, let's create the maximum. This operator outputs the maximum value from its inputs. Let's plug the noise. Then create a constant value for the second input. The output goes to the amount. Look, the maximum node compares the incoming values and chooses only the highest values from them. Since we compared the noise values to 0, the maximum node chose 0 instead of negative values, therefore in some areas of the torus, the displacement is equal to 0. Let's tweak the value of the second input. As you can see, by increasing this value, noise gradually disappears because the noise value becomes less than this value, or vice versa. There is also a minimum node, let's create it. This operator outputs the minimum value from its inputs. Let's plug the noise. Then plug the constant. And the output goes to the amount. As you already noticed, the exact opposite turned out because the minimum node selects only lowest values. Let's play with constant value again. Great, let's go on. For comparing these 2 nodes, we can use a switch node. Let's create it. This node switches between network branches based on the value of an input. First input is an integer that specifies which input to pass through to the node's output. The numbering starts at 0. Now let's connect the inputs between which we are going to switch. Switch output goes to the amount. Look, now we are switching between the 2 versions. When the index is 0, the input 1 goes through the switch node, when the index is 1, the input 2 goes through the switch node, and so on. Let's also plug the third version, which is simply the noise. Here we go, we can switch between 3 versions. Now I want to promote the switcher index at the object level. For that, let's create a parameter node. This operator creates a parameter of any vex data type and promotes at the object level. Now let's jump at the object level. Here it is, newly created parameter. Let's dive inside again. Like a constant node, we can specify all vex data types. The parameter type must be an integer. I will call it switcher. Connect this parameter to a switcher. Now let's jump at the object level and test the switcher. Excellent, we can move on. I also want to show you the shortest way to create a parameter node. First, let's delete this one. Then right-click on this port, and instead of a constant we will choose the promote parameter option. Look here, it is created, but it shows up as a small icon because it is in a hidden state by default. In order to see it as a separate node, just double-click on it. To hide back, just right-click on it, select the flags, then click on the hide node. Let's check again if everything works. Great, let's go ahead. Now I want to colorize the torus, taking into account the degree of deformation compared to the original shape. For that, let's create a subtract node. The displaced position goes to the first input, the original position goes to the second input. Subtracting these two positions, we get the difference between them. Let's plug the result of subtraction to the output position. This is a difference vector between two shapes. Okay, let's connect back the displaced position. Now we need to get the length of the difference vector. For that, let's create a length node. This operator computes the length of a 3D or 4D vector. Plug the difference vector. For coloring, we will use the ramp parameters node. Let's create it. Make sure that ramp type is specified as a color ramp. Plug the length of the difference vector. The output of the color ramp goes to the CD port. CD attribute is just a color diffuse of each point. Look, our geometry is now black and white because by default the color ramp creates a gradient between black and white. To have a bright white color, we need to fit the incoming range. Let's create a fit range node. We need to adjust only the source max. Now let's jump at the object level and set up the ramp colors. This is good for now, let's jump inside again. I want to adjust a source max again. Take a look, areas where the deformation length is 0 or tends to 0 are colored blue, and areas where the deformation length is maximum or closer to the maximum are colored red. Great, now I want to introduce you to a new node that can replace these two nodes. It is a distance node. This operator returns the distance between 2 points. In simple words, the node subtracts two vectors, then calculates the length of the difference vector. Let's connect both positions. Then plug the length to the fit node. Here we go, the result is the same. Let's get rid of these two nodes, we don't need them anymore. Now I want to show you a new node called mix. This operator computes a blend, or a mix, of its input values using linear interpolation. If the bias specified is outside the range 0 to 1, the values will be extrapolated linearly. Now let's connect both positions to it. We can temporarily delete these connections. The output of mix goes to P. Now let's play with bias. The mix node blend these two shapes. When the bias is 0, only the first shape is visible, and when the bias is 1, only the second shape is visible. In between, we get a mixed shape. Let's also override this connection by the mix output. Now we can return the colors. Let's play with bias again. Here we go, the colors are also changing. Now I propose to derive the bias with some mask. For making a mask, I will use the bounding box information. Let's type a bound and drop down a relative to the bounding box node. This operator returns the relative position of the point given with respect to the bounding box of the specified geometry. First, we have to specify in which geometry to look for the bounding box information. In our case it is the same geometry, so we will connect op input 1 to the file. Look, these 4 strings represent these 4 inputs of the attribute VOP. The first string always represents the geometry itself. Okay, we also have to give a position vector. Now we can use the relative bounding box information as a mask. Let's create a vector to float node. Connect this vector. The X component goes directly to the CD port just to visualize the mask. Look, we have a mask ranging from 0 to 1, and the mask grows along the X-axis. We can also use a mask along the Y-axis or Z-axis. To make it visually more obvious, let's create a set vector component. Connect this to the float input. The output vector to CD. Look, the mask turned red because we only connected to the first component, which is the red channel. Now let's check the masks in all directions. Okay, let's move on. In order to reverse the mask direction, you can use the complement node. Let's create it. This operator computes the complement of the argument by subtracting the argument from 1. Since the range of these masks is between 0 and 1, the complement operation reverses the mask. Okay, now let's use this mask. Move these nodes closer to the mix node. Plug the mask to the mix bias. As you can see, the noise gradually disappeared along the opposite direction of the X-axis. Let's disconnect the mask visualization. Then wire back the initial color. Okay, now let's decide in which direction to fade the noise. Let's choose along the Y-axis for now. Look, there is no noise at the bottom of the torus. We can also fit the range of the mask. Create a fit range node. Wire to this line. Playing with source max and source min, we can adjust the mask as we like. Now let's try to animate this mask. For that we need an add node, let's create it. Connect to this line, then promote the second input. Let's jump at the object level. Here is our promoted parameter. Okay, let's jump inside again. Select the parameter and put a -1 for the minimum value. Let's jump up again and tweak the parameter value. As you see, the noise disappears and reappears along the Y-axis. Now let's change the fade direction. This time I will choose along X. That's it. Everything works as it should. Okay, let's go on. The last thing I'm going to do is control the fade mask by spline ramp. Let's create it. We have to rename it because the default name already exists. The ramp type will be a spline ramp. Give it an input, then connect output to bias. Now we can jump up at the object level and set up the spline ramp. Let's check what we have now. It seems we need to reverse the spline ramp. Here we go, that's what I was looking for. We can also change the interpolation type. Let's check again. Excellent, it's the final result. The last thing I want to do is change the fade mask along the y-axis. Let's see what it looks like. Nice, I think we can stop there. In the next lesson we are going to discover a lot of new nodes, and we will delve even further into the VOP context. See you in the next lesson. Hello, this is a list of nodes which we are going to discover along this lesson. We will also use the nodes that we are already familiar with from past lessons. As we already know a lot of nodes, we will try to do something more interesting. Okay, let's get started. First, we need a grid. Let's hide the shelf as well as the playbar. Then double-click and dive inside. Put a 100 for rows and for columns. Now let's create a mountain node just to make some noise on the grid. I will adjust only the element size and height. Let's create also a Remish node to make some kind of irregularity in terms of topology. Put a 0.03 for target size. Let's also create a sphere. Put a 0.1 for scale. Look, the sphere type is a primitive. It means the sphere has only one point. Let's go on. Now we need the attribute VOP. Connect a Remish node to the first input, the sphere to the second input. Template the sphere, then jump into the attribute VOP. Now I want to introduce you to a new node called the import point attribute. The import point attribute can fetch the attribute value from the specified geometry. I want to import the point position of the sphere. Since the sphere is already connected to the second input, we must connect the second string port to the file. Well, now we need to specify the point number, the position of which we are going to import. Since the sphere has only one point, the number will be 0. And finally, we must provide the name of the attribute we are going to import. The default is p, what we need. Let's create a distance node, which we already know from the last lesson. I want to get the distance for each grid point from the sphere. Connect to both positions. Now let's visualize the distance values as a caller. For that we need the setVector component node. Connect the distance to the float value. Select the first component of the vector, which is red. Connect the output vector to CD port. Here we go, we got a visualization of the distance attribute for each point. Let's jump up the object level. Select the sphere and move it. As you can see, points that are close to the sphere tend to black because the distance values are close to 0. Okay, let's dive into attribute VOP again. Now I want to show you the alternative to visualize any attribute. First, let's delete this one. Then hold the X key and click to this port. That's it, Houdini automatically creates a visualize node, which essentially does the same thing. If necessary, we can bypass this node. You can also create this node yourself. Okay, let's go on. Now I want to invert the distance attribute. For that, let's drop down the complement node. I also want to fit it. Let's adjust the source max and source min. Something like this. now I want to show you two very important nodes. The first one is a bind. The second one is a bind export. The bind node simply imports any type of attribute that already is attached to the geometry. The bind export simply writes a new attribute in the geometry. In fact, these two nodes are one single node. The differences between them are these two activated checkboxes and the export specification. Now let's delete the bind node and leave only bind export because I'm going to write the distance as a new attribute. Connect the distance to the bind export. Give it a name. I will call it a mask. Now let's switch to a geometry spreadsheet. And here it is. The newly created attribute can be checked in another way. Hold middle click on the attribute VOP and here it is. Okay, let's dive inside again. Now I want to push up the geometry with this mask. Let's create a getVector component. Connect position to it. Then extract the Y component. Let's also create a setVector component. Select the Y component. Connect position to it. Then connect the Y component. And the output vector goes to P. Now we can edit the extracted Y component. For that, let's create an add node. Wire to this line. Let's hold down the Control key to hierarchically move the add node to the right side to make room for further work. Now let's add the mask to the Y component. Here we go. We push up the geometry in Y direction with a mask. Let's bypass the visualize node to make it more noticeable. Definitely it is too much. We can multiply the mask by some value to adjust as we need it. That's it, we can control the mask's influence. I will leave this value at 0.1. Okay, now let's jump at the object level. Let's give a name to this attribute VOP. Let's go on, now I want to create a copy to points node. Plug the deformed grid to the second input as target points. Now I want to create a sphere and connect to the first input as a geometry to copy. We copied the sphere onto these points. Let's also scale down the sphere. I also want to change the shading mode. Now let's create the second attribute VOP. Wire to this line. Give it a name. Then dive into it. Now I want to create a p-scale attribute, which is simply a uniform scaling factor. The copy to points node knows about the p-scale attribute. Let's create a bind expert node. Call it p-scale. Then create a constant. As you noticed, our spheres are gone because now their uniform scale factor is 0. Let's tweak the constant value. Here we go, the spheres are scaling up and down. Let's put a 0.2 for now. I want to temporarily give them some color. Just right-click on CD port, select the constant. Then set a 1 for the green channel. Now the spheres are more noticeable. Okay, now I want to randomize the p-scale value. For that, let's create a random node. This operator generates a random number based on the position in different dimensions. Let's connect the ptnum to the random input. The ptnum gives us the number of each point in the current geometry. Look, the random node generates random values in range from 0 to 1 based on point numbers. Let's multiply the p-scale by these random values. As you noticed, now we have a random p-scale. In order to contrast a random range between 0 to 1, let's add a power node. So, we made a contrast between the smallest and biggest p-scale. Let's also clamp the smallest values. Like so. Now I want to add a noise to p-scale. Let's create a turbulent noise. Give him a position. Then create an add node and add the noise to the p-scale. Let's adjust the noise settings. Looks like good. I also want to increase the initial p-scale. That's it. Now I want to multiply the p-scale values by the mask which we created recently. Let's create a bind node and import the mask. We have to write the correct name of the attribute and specify the type. Let's multiply the p-scale by the mask. Take a look, the spheres disappeared in areas where the mask value is 0. Now I want to fit the range of the mask. Let's play with a new range and see what it looks like. Okay, it seems good. Let's jump to the object level and check it all in action. Just select the sphere and move it. Here we go, moving the sphere the mask moves, which in turn drive p-scale. Let's move on. Now let's create one more attribute VOP. This time we will set up the color. First let's create a random node. Plug the point number. In this menu select the 3D color output. Then plug the output vector to the CD port. As you can see, now we have a random color for each sphere. We can uncheck this option. In order to change the seed of randomly generated color, we have to shift the point numbers. That's it, for each value is generated a new color. Now I want to create a color in the specified palette. First let's delete this connection. From this menu select 1D output, this means now the random node generates random numbers in range from 0 to 1. Let's also create a ramp parameter node. Plug the random values to it. The output goes to the CD port. Let's jump at the object level and set up the desired color range. Okay, it's good for me, let's go ahead. Now I want to import the mask attribute, then change the color where the mask is greater than 0. Let's create a bind node and bring into the mask attribute. Let's check the mask visualizing it. Now let's edit the mask a bit. For that let's create a selling node. This operator returns the smallest integer, greater than or equal to the argument. Wire it. Look, all values that are greater than 0 turned into 1 because the 1 is the largest integer in this range. There are two more similar nodes that also do rounding, but each in a different way. Now I will show you the second one, which is called floor. This operator returns the largest integer less than or equal to the argument. Let's create the third, called round to integer. This operator rounds the argument to the closest integer. Let's also connect the mask to these two nodes. Now I want to compare the result of these three nodes. For that, let's create a switch node. Connect all them to the switch. The output of the switch goes here. Now we see the result of selling. Let's switch to the second one, that is the floor. This time all values that are less than 1 turn to 0 because the 0 is the smallest integer in this range, so now we only have a few red spheres whose values were 1. Let's see the result of the third version. The round to integer node returns the nearest integer value. In our case, the values that are greater than 0.5 become 1 and values less than 0.5 become 0. We will use only the selling node, so let's get rid of these nodes. Now let's create a two-way switch node. This operator takes an integer input. If this input value satisfies the condition parameter, the output is set equal to the first input value. If the integer input does not satisfy the condition parameter, the output is set equal to the second input value. This provides a simple way to switch between two values and simulate an if-then-else construct. Let's set a condition based on the mask. First, let's convert the mask to the integer value because the condition port of the two-way switch node is also integer. Let's connect the mask to the condition. Then plug the ramp color to the second input, which will set the color for spheres that don't satisfy this condition. Connect the output to the CD port. Here we go, where the condition is satisfied, the color of the spheres become black because we still have not specified the color when the condition is true. Let's arrange these nodes just to organize them. Now let's create one more color ramp. Connect the mask. Let's rename the ramp because this name already exists. Connect this ramp to the first input of the two-way switch node. Great, we just have to set the ramp colors. Okay, that's good for me. Let's see how it looks in action. Looks good, but I want to tweak the p-scale attribute a bit. Let's test it again. And finally, I want to adjust the mask range. That's it, let's check again. Here we go, now everything suits me. Okay, that's all for this lesson. We will continue to discover new nodes in the next lesson. Hello, this is a list of new nodes which we are going to discover along this lesson. Since we already know a lot of nodes, this time we will try to do something more complex and interesting. Okay, let's get started. Create a torus. Dive into it. Put a 200 for rows, 400 for columns. Let's create normals, as we are going to use them soon. We will store them in points. You can check the normals by pressing this icon. Okay, let's go on. Let's drop down the attribute VOP. Wire the geometry and dive into it. Now we will use a new node called dot product. This operator computes the dot product between two vectors. Look, in simple terms, when we have two normalized vectors that are parallel to each other and both are directed in the same direction, their dot product will be 1. In case when we have two normalized vectors that are parallel to each other but are directed in opposite directions, their dot product will be -1. In case when we have two normalized vectors that are perpendicular to each other, the dot product will be 0. In other cases, the dot product varies between -1 and 1. Now I want to demonstrate in practice what it looks like. First, let's split the viewport like this. Then, switch to the geometry spreadsheet. Let's dive in again. As the first vector, we connect the normals. For the second one, let's create a new vector directed up. Let's visualize the result of the dot product. From the color, it is clear that at the very top of the torus, the dot product is approaching 1 because the normals become parallel to the given vector and look in same direction. At the bottom of the torus, the dot product is approaching -1 because the normals become parallel to the given vector, but they are directed in opposite directions. When the normals become perpendicular to the given vector, the dot product tends to 0. Let's export the dot product as a new attribute and check the result in the geometry spreadsheet. Take a look, the maximum value is 1, minimum -1. Let's hide all attributes. Then display only this. That's it, we can move on. Now let's change the second vector direction along -y. As you noticed, we get the opposite result. Let's try one more direction. I want to show you an easy way to set any direction you like. Create a transform matrix. This node transforms an input position, normal, or vector by a matrix specified by the translate, rotate, and scale parameters. Now we can rotate this vector around any axis and get the desired direction. Okay, now I want to show you why we need normalized vectors. Since both vectors are normalized, let's change the length of the normals by multiplying some value. As you can see, now the result of the dot product is out of the range of -1 and 1. Now let's normalize the normals. This operator normalizes a vector. Here we go, the dot product is in the range -1 and 1. The same applies to the second vector, let's quickly check this case too. That's it, we can move on. Let's get rid of this extra node, we don't need it anymore. I want to rename the exported attribute. Call it mask1, later we're gonna use this mask. Now I want to edit this mask a bit. For that, let's create a turbulent noise. Give it a position. Let's visualize the noise 1D output. Change the noise type just to generate positive and negative values. Let's also increase the frequency. Look, we generate values in the negative and positive range. Okay, now I want to introduce a new node called sine. This operator returns -1 if the input is less than 0, otherwise it returns 1. If the input value is 0 exactly, 1 will be returned. Look, all negative values became -1, and all positive values became 1. It means now we have only two values, 1 and -1. To shift the mask in a positive or negative direction, we can simply add positive or negative values. Here we go, we control the amount of positive or negative values. I want to clamp this mask and get 0 instead of -1. Now we have only 0 and 1. Visualize the dot product. I want to get rid of the negative values of the dot product too. Let's clamp these values also. Okay, all negative values became 0. Now I want to multiply the result of dot product by the noise. Here we go, we have noise at the top, and at the bottom it disappears. We're gonna use this mask soon. Let's jump at the object level and give a name to this attribute VOP. Now let's create a scatter node and generate points on the torus. Let's change the point count. I think better to return the default, which is 1000. Disable relaxed iterations. Enable the density attribute and give a mask. Here we go, the mask controls the density of points, so in the areas where the mask is 0, we have no points. Okay, now I want to copy some geometry at these points. Let's use a tube. I want to adjust tube properties. Now let's connect tube to the copy node. Let's also template the torus geometry. As you can see, the tubes are directed along normals. To make sure, let's disable and enable the normals. Let's adjust tube settings to get a more interesting shape. Look, the tubes penetrate the torus. To solve this problem we have to move the tubes along the z-axis. To make them sit on the torus, we can copy the height value. Paste it here, then divide by 2. Now we can adjust the height. Let's also decrease the radius scale. Great, let's move on. Now I want to create one more attribute VOP. Wire to this line and name it a p-scale setup. Dive into it. Now I want to create a p-scale attribute and then start to manipulate it. First, let's create a bind export. Name it p-scale. Let's also bind the mask attribute which we recently created. We called it mask1. Connect mask to the p-scale. Looks not bad. Let's also add some randomization. In this time we will use a Gaussian random node. This operator generates a random number fitting a Gaussian distribution. Plug to it the pt num. Let's write the result of the Gaussian random node as a new attribute and see what it looks like. I will name it ran test. Open the geometry spreadsheet window. Hide all attributes. Then check the ran test attribute. Take a look, the Gaussian random node generated the random values in the negative and positive range. The sigma parameter controls the length of the range in positive and negative directions. To squeeze the range we must reduce the sigma, and to stretch the range we must increase it. Now we can delete the bind export node. Let's create an add node. Wire to this line, then add random values. I also want to adjust the sigma parameter. In order to avoid a negative p-scale, which will cause us to get inverted normals, we can add a maximum node and exclude the negative values. For the second input, let's put some small value. The maximum node will always pick 0.15 if the first input is below this value. Now I want to increase the p-scale value only for a certain percentage. For that, let's create a ramp parameter. Choose a spline ramp. We also need the random node. Connect to it the PT num. The random values connect to the ramp. Now let's add these random values to the p-scale. As you noticed, nothing has changed because the default spline ramp is 0. Let's jump at the object level and set up a spline ramp. Choose a constant for interpolation type. Now we can control the percentage of random values that are not 0. That's it, so simple. Let's put a 0.95, which means we increase the p-scale only for 0.05% of tubes. Definitely, some tubes are very large. Let's do the final adjustment. We can fit the random values. Squeeze the new range from 1 to 0.5. Looks fine, we can move on. Now let's create a one more attribute VOP. This time we will set up the color. Dive in. I want to give a color based on the mask attribute. Let's bind the mask. Create a color ramp and plug the mask into it. The output of the color ramp connect to the CD port. Let's jump at the object level and set ramp colors. Looks cool. Now we can dive inside the attribute VOP and start to manipulate these colors. Create a hue shift node. This operator shifts the hue of the input color along the color wheel by the amount of the shift value multiplied by the amplitude. Plug to it the color. The output color connect to the CD port. Make a 1 the shift amplitude. Look, we can shift the hue of the input color. Okay, now I propose to drive this parameter by the time. First, let's create a sine node. Plug to it the time. Then we have to fit the sine output range. Look, the source range is -1 to 1, we shift it from 0 to 1. Now we will drive the hue shift with this modified time. Toggle real-time button, then play the animation. As you can see, the time cyclically shifts the hue input color. Okay, now let's delete these two nodes and try to drive the hue shift in a different way. This time let's use a relative bounding box information. Create a getVector component node, then extract a relative bounding box along X. Now let's shift the hue of the input color by the bounding box information along X. That's it, looks nice. We can also control the shift amplitude. Great, let's continue. Now I want to show you another cool node, which is an alternative to the hue shift node, and it is more advanced, with which you can manipulate the colors as you like. It is called color correction. This operator provides a means to change the hue, saturation, intensity, bias, gain and gamut of the input color. Plug to it the ramp color. The output color connect to the CD port. Look, now we can shift the hue. We also can control the saturation, as well as the color intensity and so on. Now let's randomize the hue shift for each point. This time, I will use a Gaussian random node just to generate positive and negative random numbers. Plug in the PT num. Decrease the sigma just to squeeze the range. Now let's drive the hue shift by these random numbers. That's it, as you can see we shift the hue randomly for each point. Let's tweak the sigma and see what it looks like. Looks cool, let's move on. Now I propose to animate these tubes. Let's jump at the object level and create one more attribute VOP. Call it animation setup and jump into it. To animate the tubes, we have to animate the normals because the tubes are directed along normals. To make sure, let's simply change the normal direction and see what happens. Create a constant node. Select a 3 floats vector. Set a direction along y and plug to the n. N is a normal vector for each point. As you can see, now the tubes are directed along y. Let's change the direction of the normal to make sure that tubes follow the normals. That's it, now let's try to manipulate the normals in a more interesting way. Create a cross-product node. This operator computes the cross product between two vectors, defined as the vector perpendicular to both input vectors. In simple words, when we have two vectors, the dot product will make a vector that is perpendicular to both of them. Let's plug the normals as a first vector. For the second vector, let's create a constant directed in a positive y direction. Now the cross product node make a new vector that is perpendicular to the given vectors. Here we go, the tubes are flowing tangentially around the torus. To reverse the direction, let's change the order of input vectors. You can simply select the node and press Shift R. That's it, we reverse the direction. Now let's jump at the object level and see how the normals look. Let's display the scatter node and check the point normals. Normals also flow tangentially around the torus. Okay, let's move on. I want to adjust the tube properties a little. Let's put a 0.5 for the second radius. Then dive inside again. Now let's create one more cross product to get the double cross product between the normals and the result of the first cross product. Look, now the tubes flow tangentially from bottom to top. Let's press the Shift R to reverse the direction. The tubes flow tangentially from top to bottom. Okay, now let's delete these nodes and try to animate the normals. Let's create an anti-aliased noise. This noise can take on a 4D vector, which gives us an advantage for animating the fourth component. Let's choose a 4D input and 3D output from this menu. Take a look, these parameters became yellow because in the VOP context 4-dimensional vectors are specified yellow. Let's create a vector to vector 4. This operator converts a vector to a vector 4. Plug to it the normals. The 4D vector connect to the noise position. Add the noise to the normals. Connect sum to the n. Take a look, now we can animate the fourth component and make them move. Let's drive the fourth component with the time. That's it, they move when the animation is running. Let's tweak the noise amplitude and see what it looks like. We can tweak the frequency as well. Now I propose to add another vector with which we can imitate the directional wind. Let's direct it along X. Here we go, now they are curved along the X-axis, as if the wind is blowing. Of course we can control the wind influence by changing the X value. We even can animate the wind influence. For that, let's create a multiply node. As well as create a fit range node. Plug the frame to it. The frame is a current frame being processed. Look, since animation timeline starts at frame 1 and ends at frame 240, let's set the source min 1 and source max 240. We just fit this range from 0 to 1. Let's also create a spline ramp. Select the spline ramp. Wire to the ramp and multiply by this. Okay, now let's set up the spline ramp. Something like this. Let's check what it looks like in action. Great, as you can see the influence of the wind changes. Let's dive in and increase the wind amplitude. That's it, the wind effect's much stronger. Let's put a -2 just to reverse wind direction. Okay. That's all for this lesson. In the next lesson we are going to discover a lot of new nodes, and we will deal with orientation. Hello, this is a list of new nodes, which we are going to discover along this lesson. This lesson is completely dedicated to work with the orientations by the quaternion. Let's get started. Since we are going to be working with orientation, I've prepared and advanced this simple geometry that looks like a 3D axis. With this it will be easy for us to identify around which axis the rotation will be. Okay, let's jump into it. I just created a subnet to hide the nodes that are used to build this geometry. Let's go on. Now let's create a grid, then copy this geometry to each point of the grid. Select points just to remove geometry but keep the points. Now let's copy our geometry to these points. That's it, now let's create an attribute VOP. Call it orient setup, then dive into it. Okay, now let's create a bind export node, just to create a new attribute. We name it orient. The attribute type must be a 4 floats, or so-called vector 4. The copy to points node knows how to handle the orient attribute. Now let's create a quaternion node. This node takes an angle and an axis and constructs the quaternion representing the rotation about that axis. In simple words, quaternion is a 4-dimensional vector that describes a rotation in 3D space. Okay, let's see what it looks like in practice. Connect the quaternion to the bind export. Look, this is the axis around which the rotation should be. In this case, it is an x-axis. The angle is an amount of rotation around a given axis. Now let's tweak an angle. As you can see, they all rotate around the x-axis. Now let's set a z-axis and rotate again. Here we go, now they all rotate around the z-axis. By default, the angle is measured in radians. In case you want to work with degrees, there is a node that converts degrees to radians. This operator converts degrees to radians. Take a look, now the angle is measured in degrees. You can also do opposite. This operator converts degrees to radians. Let's delete both, we don't need them anymore. Now I want to randomize the axis around which the rotation occurs. Plug in the PT num. Select the 3D vector. Then plug to the axis. Now let's tweak the angle and see what it looks like. As you can see, they all have a random rotation axis. Now let's keep these random orientations, then try to rotate them around the local axis. For that we will create a quaternion multiply node. This operator performs a quaternion multiplication with its two inputs. We also need one more quaternion. Plug both quaternions to the multiplier. The output goes to the bind node. Look, now they are all rotating around the local x-axis. Now let's change the rotation axis. Instead of the x, let's set the z. Here we go, they are all rotating around the local z-axis. Now I want to do the same thing in a different way. First, let's select all these nodes except the bind export and delete them. Now let's create a Euler to quaternion node. This operator builds a quaternion with the given Euler rotation. The input has to be in radians. Connect to the bind node. Look, now we can rotate them around any axis. Okay, now let's randomize their initial orientation. We also need a quaternion multiply node. As well as let's create a one more Euler to quaternion. Multiply each other and plug to the bind export. Now let's test our setup. As you can see, they are all rotating around local x. Let's try also around the z-axis. Here we go, we did the same in a different way. Now I want to show you some simple ways to randomize the orientation for each one. Let's delete all this again. Then create a turbulent noise. Plug to it P. Select original Perlin noise. As well as we need a 3D noise. Now let's create a vector to quaternion. This node converts the vector to quaternion. Let's plug in the noise. The quaternion goes to the bind export. Now let's tweak noise amplitude and see what it looks like. That's it. With the amplitude of the noise, we can control the amount of rotation. Of course you can control the noise frequency, offset, and so on. Okay, now I want to show you a short and simple way to generate random orientations. Let's create a random node. Plug to it the PT num. Then choose a 4-dimensional output. Plug to the bind export. Here we go, we have random orientation for each of them. Now I want to do something more complex with quaternions and in the process show you another important node related to quaternions. Let's delete this node. Then create a quaternion node. Plug it to the bind export. I want to draw the angle by time. Let's play the animation and see what we get. Toggle the animation in real time. Let's increase the rotation speed by multiplying the time by some value. Now the rotation speed is good for me. Let's create another quaternion node. For this one we will keep the default properties. Let's plug it to the bind export and see what we get. Okay, let's return the old connection. Now I want to introduce you to the quaternion distance node. This operator computes the angular distance between two quaternions, measured in radians. Let's connect both quaternions to it to measure the angular distance. Now I want to export the angular distance as a new attribute and see what it looks like. I will name it quat_dist. Now let's open the geometry spreadsheet. Hide all attributes, then display only quat_dist. Let's run the animation and observe how this attribute changes. Look, between them the angular distance increases and then decreases. The transition moment is a semicircle. The semicircle in radians measured 3.14. In degrees it will be 180. Actually we can convert the radians to degrees. Let's run animation and check the quat_dist attribute. Here we go, the angular distance increases to 180 degrees, then starts to decrease. Excellent, we can move on. Now I propose to use the angular distance to drive p-scale. First, let's fit the range of angular distance. The source range must be from 0 to 180. The destination range will be from 0.25 to 1.5. Now let's create a p-scale attribute and drive with this modified angular distance. Great, let's run the animation and see how it looks. It doesn't look good so far. I propose to shift the p-scale with some interesting mask. I'm going to use the relative to bounding box information. Give it all the inputs it needs. Now let's create a getVector component and extract the relative to bounding box information along x. Now let's add this mask to the time that drives the rotation. Before adding, let's add a fit range node to get an additional control. Here we go, now they rotate and scale unevenly. Of course we always can control the mask range. Let's put a 1.5 for now. I also want to increase the global rotation speed. Let's multiply by 4. Okay, looks good, we can move on. Now let's create a color and try to manipulate it with an angular distance. We need a fit range node, let's create it. Then plug the angular distance to it. Put a 180 here. Now let's create any color, then start to modify it. To edit this color I'm gonna use the hue shift. Plug to it the color. The output goes to the CD port. Let's make 1 the shift amplitude. Now I want to drive the shift amplitude with angular distance. Connect the angular distance to the shift amplitude. Here we go, we got a variety of colors, it will look more interesting during animation. Let's play the animation and see what it looks like. Looks nice. Of course we can reduce the shift amplitude and achieve less color variation. Now I want to change the rotation axis and see how it looks. Let's set a y-axis. Not bad too. Let's also try around the z-axis. Looks more interesting, but I want to inverse the rotation. For that we can use a quaternion invert node. This node outputs the inverse of the input quaternion. This will rotate vectors in the opposite direction. That's it, now they rotate in the opposite direction. Okay, let's go on. Now I want to add some randomization during the rotation. For that I will create a random node. Plug to it the PT num. Create a multiply node. Then connect to the time. Let's also create a fit range node, then plug to it the random values. Put a 0.75 for destination min. Then multiply these random values by time. Now let's run the animation. As you can see, we randomize the rotation order. Let's reduce the impact of randomization by increasing the destination value. Looks cool, but I want to decrease the impact of randomization even more. Let's put a 0.9 and do a final look. Looks great, let's go on. I want to do final correction. This time I want to increase the shift amplitude. Cool, I like it. Now I propose to stop at this and start something new in the process of studying other nodes related to the quaternion. Okay, this time I'll be using this simple torus, which I've pre-assigned a color to make the rotation around the y-axis more noticeable. Well, let's create an attribute VOP. Connect the geometry to it, then dive inside. Let's create a rotate by quaternion. This node rotates the provided vector by the quaternion. Since the input is treated as a vector, it is a rotation around the origin. The quaternion should be normalized. To rotate by quaternion we can use Euler to quaternion. We will rotate the position vector. Plug the output vector to the P. Look, we can now rotate geometry around any axis using a quaternion without an orient attribute. Since the center of torus matches with the origin, everything is perfect. Let's jump at the object level and move the torus away from the origin. Now let's rotate again and see what it looks like. As you can see, we have a problem. The torus continues to rotate around the origin. What if we want to rotate the torus about its center? Let's jump at the object level again. Create an extract centroid node. Connect the geometry. Select a detail. Here we go, we extract the centroid. Press D on viewport, go to the geometry menu tab, then increase the point size. Now the center point has become much more noticeable. Plug the centroid point to the second input, then dive inside. Now let's create an import point attribute. Connect to it the second geometry, which is a centroid point. Since the second geometry has only one point, the point number will be 0. Okay, now we import the centroid position. I'm going to move the torus to the origin. For that we just need to subtract the center position from the point position. Here we go, the torus is at the center coordinate. Now the rotation is correct. It means we can return the torus to the initial position before rotating it. Now let's add centroid position before the rotation. That's it, the torus jumped to the initial position. Now let's rotate it and see what we get. As you can see, we have a correct rotation regardless of the location of the torus. Let's jump to the object level and reposition the torus, just to make sure our setup always works correctly. That's it, all work as it should. Okay, now let's see the case when we have a lot of geometries and we need to rotate all of them around local centers. First, let's copy these two nodes. Then create a copy and transform node. Let's copy the torus 5 times. Then move along the x-axis. Now we can copy them again, along the z-axis. Excellent, we can continue. Let's drop down the attribute VOP. Wire to it the geometry and dive inside. Create a rotate by quaternion. Plug to it the position. Create a Euler to quaternion. Plug to the quaternion input. The output vector goes to the P. Now let's rotate by quaternion and see what we get. As you can see, all toruses rotate around the origin as one solid piece. Now I want to make them all rotate around their centers. To do this, we can use the same method which we did recently. Let's create a connectivity node. Connect to this line. This node creates an attribute with a unique value for each set of connected primitives or points. The default name for the attribute is class. Look, now we have a unique attribute for each torus called class. Later, based on this attribute we can identify each torus inside the attribute VOP. Now let's create centroid points for each torus based on the class attribute. Wire to it the geometry. Since the class attribute is stored in points, we have to specify the point. Select the class attribute from which the centroid points will be generated. Excellent, here they are. Connect the centroid points to the second input. As you can see, the centroid points are inherited the class attribute. Excellent, let's dive inside. Now let's create an import point attribute. Plug to it the op input 2, which represents centroid points. Now we need to set point numbers. We can determine the point numbers by class attribute. Let's create a bind node and bring in the class attribute. The attribute type is an integer. Type a class. Okay, now let's connect the class to the point number. Excellent, we imported the centroid point positions. Now we need to subtract the centroid positions from the torus's positions in order to simply move the toruses to the origin. That's it, they all jump to the origin. After rotation we can already return them back by adding the centroid positions. Here we go, they return to their original places. We can press Alt, then click on the wire just to add a dot, then reshape. Now we can rotate by quaternion and see what we get. Great, they all rotate around their centroids. Okay, now I want to randomize the rotation of each torus. For that let's create a random node. I want to generate the random vectors based on the class attribute. From this menu select the 3D vector output. Now let's create a turbulent noise. Plug to it the random vectors. Select the original Perlin noise. The output should be a 3D vector. Excellent, now let's increase the noise amplitude. Then plug the noise to the rotation vector. That's it, we got random orientation for each torus. You can control the rotation amount by noise amplitude. Now I propose to stop this setup and start doing something new, during which we will learn a lot of cool things related to quaternions. Okay, let's get started. This time we are going to use this simple box that I prepared in advance. Now let's create a line. Put a 50 for points. Change the direction along X. Put a 15 for length. Excellent, let's create a copy to points node, then copy the box onto the points of the line. Let's drop down the attribute VOP. Wire to this line. Then dive inside. Now I want to introduce you to the new node related to quaternions, that is called spherical linear interpolation. This operator computes a spherical linear interpolation between its two quaternion inputs and outputs the intermediate quaternion. This interpolation will always be along the shortest arc. Let's leave it temporarily, we will need it soon. Drop down the bind export node and create an orient attribute. The attribute type must be vector 4. Let's also create a quaternion node. Then connect to the bind export. Now I want to gradually rotate the boxes around the x-axis. For that, let's create a gradient from 0 to 1 along the line. To get this gradient, we can divide the number of points by the total number of points. The num-pt is a total number of points in the geometry. Look, the output of the divide node is integer because the first input is also integer. Since we are going to create the gradient from 0 to 1, this should be a float. Let's convert the first input from integer to float just to have float output. This operator converts an integer value to a float value. That's it, now let's export this attribute and see what we get. I call it curve mask. Let's open up the geometry spreadsheet and check this attribute. Look, we have a gradient from 0 to 0.98. The maximum value will be 1 if we subtract 1 from the total number of points because the point numbers start from 0. Okay, let's create a subtract constant. By default, this node subtracts 1, which is what we need. Let's check the curve mask attribute. Here we go, the mask range has become from 0 to 1. Okay, let's go ahead. Now let's delete the bind export node, then plug this to the angle. To expand or narrow this range, we can create a multiplier. Here we go, we can rotate gradually as we like. Now I want to give them nice colors. Let's create a hue shift node. Connect the output color to the CD. The default color will be red. We are going to shift the red color by this range. Let's tweak the shift amplitude. That's it, we got nice color gradients along the line. We can arrange the nodes a bit to make the setup more readable. Now it's time to use the spherical linear interpolation node that I temporarily left. First, let's create a quaternion invert node. Invert the rotation. Take a look, we got exactly the opposite. Let's get the original rotation back. Now I'm going to interpolate with inverted. Connect both quaternions to it. The output quaternion goes to the bind export. Let's tweak the bias. Here we go, we can blend two quaternions. Now I propose to blend them in an interesting way. Create a ramp parameter. Select the spline ramp. Connect to it this range. The ramp output goes to the bias. Now let's edit the spline ramp. Okay, something like this, mixing occurs only in the middle. Now I propose to shift the input ramp range and see what we get. Let's create an add node. Promote the second input. Let's give it a name. Put -1 as the minimum limit. Now let's tweak this parameter. Here we go, by moving this parameter we shift the region where the blending occurs between the two quaternions. Okay, let's continue. Now I want to edit the color based on the distance between the two quaternions. For that we need a quaternion distance. We are going to measure the distance between the initial quaternion and the blended quaternion. Excellent, now we can use the distance as a color multiplier. Create a multiply node. Before multiplying, let's fit the distance. Put a 1 for destination min and 10 for destination max. Now let's multiply the color by the distance. Excellent, let's check how it looks in action. So, in a region where the mixing occurs, the color intensity increases 10 times. Great, the last thing I want to do is change the p-scale where the blending occurs. Now let's create a p-scale attribute. We need one more fit range node. Connect to it the distance. Put a 1 for destination min and 1.5 for destination max. Then connect it to the p-scale. Let's do a final look. That's it, the p-scale also changes where the mixing happens. Well, let's stop at this. We are practically studying all the main nodes associated with quaternions. In the next lesson, we will study matrices that give us an alternative way of doing similar things and more. Hello, this is a list of new nodes which we are going to discover along this lesson. This time the list of new nodes is small, but the lesson is very informative. Whole lesson is about matrices, which give us enormous potential to manipulate geometry. Excellent, let's get started. Create a torus. Jump into it. Put a 50 for rows and 100 for columns. Now let's remesh this geometry just to get triangles. Put a 0.16 for target size. We can also increase the amount of iterations. Now let's create a facet node. Connect to it the geometry. Let's toggle the unique points checkbox just to detach all triangles from each other. To make sure that they are all separated, we can simply use an exploded view. That's it, all triangles are separated. Now I want to extrude the triangles just to give them a little thickness. Let's also toggle this checkbox just to have back faces. Okay, now let's connect the extruded geometry to the exploded view and see how it looks. That's it, they all have a little thickness. We can already delete this node, we no longer need it. Now let's drop down the attribute VOP. Connect to it the geometry, then dive inside. Okay, before I start working with matrices, I want to quickly colorize this geometry. For that I'm going to use relative bounding box information. Let's give it all the necessary inputs. Then, connect the output vector directly to CD. Here we go, we get a nice color gradient along 3 axes. To saturate the colors, we can use the power node. Let's increase the exponent parameter. That's it, we got more saturated colors. Okay, now we can start working with matrices. First, let's create a translate node. This operator translates a 4x4 matrix by amount vector along the XYZ axis. In order to translate this geometry, we have to multiply the position vector by the matrix. Take a look, now we can translate the geometry along any axis. Since we won't touch color anymore, I suggest drag away these nodes to make room for further workflow. We can duplicate the geometry VOP output. Hold Y key and drag over this wire just to break the connection. This one also. Look, now we have 2 geometry VOP output nodes. On the first one, the position vector is connected, on the second one, the color vector is connected. Well, let's arrange the nodes and move on. Now I want to introduce you to a rotate node. This operator applies a rotation by radians to the given 3x3 or 4x4 matrix. Axis specifies the axis of rotation, which can be an arbitrary direction and must be normalized. Now let's multiply the position vector by the rotation matrix. Look, now we can rotate our geometry around any axis. In fact, it does the same thing as a rotate by quaternion node. Now I want to introduce you to the scale node. This operator scales a 3x3 or 4x4 matrix by amount vector along the XYZ axis. Now let's connect the output matrix to the multiply node. As you can see, we can scale up and down our geometry. Of course we can scale along an individual axis. Look, with these 3 nodes, we can move, rotate and scale as we like. Now I want to show you how important the order of these 3 operation is. Let's move the torus away from the origin, then try to rotate it. As you can see, the rotation occurs around the origin. Let's check the scale as well. Look, the scale also occurs relative to the origin. Now let's delete these connections, then start ordering in a different way. The first will be scaling, rotation will be the second, and the third is already translating. Now let's check what we have. The scale works correctly considering the orientation in space. The rotation occurs correctly around the center of geometry. The translation also works as it should. Okay, let's return the default values for all of them. Now I want to manipulate each extruded triangle separately. Let's jump at the object level. I'm going to do the same trick which we did with quaternions, extract the centroids for each piece. For that we need a unique attribute for each piece that can be generated by the connectivity node. The unique attribute is a class. Now let's create an extract centroid node. Select a point, then specify a class attribute. Here they are, the centroid of each. Connect them into the second input, then dive inside. Let's organize the workspace a bit to make room for further workflow. Select all nodes associated with colors, then create a network box. Call it Color Setup. Then minimize the network box. We hide the nodes because we are not going to touch them. Now let's drop down the Import Point Attribute node just to bring in the centroid positions. Connect to it the second geometry. We have to specify the point number. In this case, a unique attribute called class must be used as point numbers. Let's create a bind node and bring in the class attribute. The type is an integer. Connect it to point number. OK, we import the centroid positions. Now I'm going to subtract the centroid positions from point positions just to move each piece to the origin. Excellent, they are all in the origin. We are going to return them to their original position after matrix multiplication. Hold Alt and click just to add a dot and change the wire shape. Here we go, we have returned the original position of each piece. Let's tweak the scale matrix properties and see what we get. As you see, all pieces are scaled relative to their centroids. Now let's tweak the rotate matrix. Look, the rotation also occurs around its centroids. Excellent, now I want to scale each piece randomly. For that, let's create a random node. Plug a class attribute to it. Now we have random float values for each piece. Since the scale amount is a vector, we can turn each random value into a uniform vector. To do that, we just need a float to vector node. Connect random output to 3 components just to make a uniform vector. The output vector to amount. That's it, we scale each piece randomly, and they all have a uniform scale. Now I suggest using some noise instead of a random node and see what it looks like. Let's create a turbulent noise. Plug the centroid positions to it. We need one more float to vector node, let's create it. Connect the noise output to these 3 components. The output vector to amount. Let's also adjust the noise amplitude. Here we go, now we scale them based on the noise. Looks nice, let's go ahead. Now let's disconnect the scale vector and start to manipulate the rotate matrix. For rotation, I'm going to use the bounding box information. As you remember, in this setup we have already imported the bounding box information. We're gonna use it again. Let's create a getVector component node. Plug the bounding box vector to it, then extract the X component. Now we're going to use this information to manipulate the rotation matrix. Plug it to the rotation angle. Here we go, the rotation gradually increases in the direction of the x-axis. To control the magnitude of the angle, we can simply add multiplier. Okay, now let's rotate them along the y-axis. I think in this case it is better to delete the multiplier. Look, there is no rotation at the bottom of the torus. At the top we have a maximum rotation. That's it, let's move on. Now I'm going to manipulate the translate matrix. Let's create a turbulent noise. Plug to it the centroid positions. Select the original Perlin noise. The output must be 3D noise. Let's get the turbulent noise closer to the translate matrix. Then plug the noise to the translate amount. Now let's adjust the noise settings. Excellent, we are able to translate each piece locally. Let's also add the rotation we just created. The only thing is to change direction along the X. And finally, let's add a scale. Here we go, this is a combined result of manipulation of all three matrices. Sure, it looks weird right now, but you can do cool things using these techniques if you want. Okay, we can continue. Now disconnect all manipulations to return the torus to its original state. This time I want to show you how you can rotate each piece around an arbitrary vector. As an option I will use torus normals. For that let's jump at the object level, then create normals. I will store them at points. We have to transfer normals onto the centroid points. Let's display the normals and see how they look. That's it, now let's transfer to the centroid points. For that we can use an attribute transfer node. Plug the normals to the second input. Specify the normals from here. We can disable the primitives. Now let's check what we get. Here we go, the normals are transferred on centroid points. Okay, now let's dive inside and bring in these normals. Create an import point attribute. Connect the second geometry to it, which is centroid points. As point numbers we have to use the class attribute. We just need to specify the name of the attribute that we are going to import. Now let's drag this node closer to the rotation matrix. Connect the normals to the axis. Now let's tweak the angle and see what we get. Take a look, all pieces rotate around the normals. To avoid the overlapping, let's scale down a bit each piece. I think it's enough, now let's rotate them again. That's it, now it is clearly visible that they rotate around the normals. Okay, let's go ahead. Now I want to show you another way to perform similar matrix manipulations, during which you will learn new nodes and new techniques. Okay, let's drop down a new attribute VOP. Connect the torus to the first input. The centroid points to the second input. Let's give names to both attribute VOPs. This time I also would like to start with colors. First, let's bring in the class attribute. Now let's generate the random values based on the class attribute. I also want to fit the range of random values. Make the destination range from 0 to 2. Now I'm going to round the random values from 0 to 2 to get integer values. Let's export the result and see what we get in the attribute spreadsheet. I call it a test. Take a look, after rounding we got 3 integer values, 0, 1 and 2. Okay, let's go on. Now I want to generate 3 random colors based on these 3 integer values. Delete the bind expert node. Then create a random node. Connect to it the 3 integer numbers. Then select 3D color output and connect to the CD this color. Here we go, we got 3 random colors. Let's create an add constant just to add a seed. That's it, now we are able to change the colors. To change the total number of colors, we just need to change the destination range. Now let's put a 1, just to get 2 colors. Let's tweak again the seed and see how it looks. Now let's add a few more colors. Put a 4 for destination max. Here we go, now we have 5 colors. Let's again tweak the seed and see different variations of these colors. Nice. Let's choose one of them and move on. That's it, I will stick to this one. Now organize this network a bit. Let's copy this one for further workflow. Then select all these nodes with regards to color setup and create a network box. Let's call it a color setup. Press C and choose a black color for the network box. Then minimize it just to free up a lot of workspace. Excellent, now let's get back to matrices. Let's create a make transform node. This operator builds a general 4x4 transform matrix. In this menu we can specify the order of translation, rotation and scale. Now let's multiply the position vector by this matrix. Look, now we can move, rotate and scale our geometry using only this single node. We even have a pivot that allows you to rotate and scale the geometry around it. Now let's import centroid points and use them as pivots. Connect to it the second geometry. As a point number we have to use the class attribute. Now let's connect the centroid points to the pivot. Let's check out what has changed. As you can see, each piece rotates about a pivot point, which in our case is the centroids. The same goes for scaling. The presence of a pivot simplifies the process since there is no longer a need to send all the pieces to the origin for further manipulation, then return them back. Okay, let's move on. Now I want to apply the transformation matrix only for specified pieces. I propose to group the centroid points, then use this group as a trigger in the attribute VOP. The group type must be points. I will call it an object because I'm going to group by object. Disable the base group, then enable keep in bounding regions. Choose a bounding object. Now we have to create some geometry and specify it as a bounding object. Let's choose a polygon. Increase the frequency. Then connect it to the second input. That's it, we have grouped all the points that are inside this sphere. Now let's move the sphere so that some part of these points remain outside. Okay, something like this. Here is our group inside 138 points. Now let's dive inside attribute VOP, then use this group as a trigger. To import a group, we can use the inGroup node. This operator returns 1 if the pointer primitive is in the group specified by the string. We must connect the geometry where the group is located. Let's enter the name of the group we are looking for. As a point number we have to use the class attribute. Now let's export the output of the inGroup node and see what we have. Call it test, then jump to the geometry spreadsheet. Look, we have 0 and 1. 0 means points are outside the group. 1 means the points are inside the group. Excellent, now we can use these values as a trigger. Let's create an if block. This block, which contains these two nodes, is a simple if construct. Look, if the condition is true, then all the manipulations that we are going to do inside this block will be performed. Now I want to demonstrate to you how it works. First, let's give it a condition. Then create a constant. The constant type is going to be a color vector. Let's make it red. Then connect the color to the if block input. Now let's copy the geometry VOP output. Delete this connection. Then connect the color to it, already inside the block. Look, the pieces for which the condition is true became red. Now let's move the sphere, which we use to group the centroid points. Here we go, pieces that fall inside the sphere turn red. Now I propose, instead of changing the color, to make some manipulation with matrices. Okay, let's get rid of these two nodes, we don't need them anymore. Unplug this, then drag these nodes close to the if block. Excellent, now let's connect the position vector to the if block. Connect the same position vector to the multiply node, already inside the block. The product goes to the output. And finally, connect the block output to the P. We can arrange the nodes to avoid confusion. Now let's tweak the scale of the transformation matrix and see what it looks like. Here we go, only pieces for which the condition is true are scaled. Let's temporarily zero the scale. Then start moving the grouping sphere. That's it, the pieces that fall inside the sphere disappear because their scale becomes 0. Now I want to rotate them instead of scaling. Let's put a 1 for scale. For rotation, I'm going to use a noise. Let's drop down the turbulent noise. Connect the centroid positions to it. The output should be 3D noise, and the type will be original Perlin noise. Put a 360 for amplitude. Then connect the noise to the rotation. Okay, now let's move the grouping sphere and see how it looks. Definitely something is missing here. I suggest improving this setup and adding rotation fade closer to the surface of the grouping sphere. Okay, now we need a XYZ distance node, let's create it. This operator finds the distance to the closest primitive on the given geometry file. Connect the third geometry to it. Then jump to the object level and connect the grouping sphere to the third input. Now we must specify the positions from which we want to measure the distance relative to the sphere surface. Let's visualize the distance and see what it looks like. Look, closer to the surface of the grouping sphere the color becomes black because the distance tends to 0. Excellent, now I suggest using this distance attribute as a mask. Delete the visualize node, we no longer need it. Now we can multiply the noise by this distance attribute. Before multiplying, let's fit the distance. Let's adjust the source max. That's it, let's check what we got. Great, now the pieces rotate gradually, and we can control the sharpness of this gradient by editing the distance attribute. That's it, this concludes this lesson. The next lesson is also devoted to matrices. We will study other important nodes associated with them. Hello, this is a list of new nodes that we are going to discover along this lesson. We will not just study these nodes, but take in practice each of them for its intended purpose. At the end we will extract the transformation matrix from the animated object. Okay, let's get started. This time I'll use a pig head. Let's dive inside. Remove this checkbox just to get rid of the shader. Put a 10 to uniform scale. I want to make the background black. Press D in the viewport, then go to the background menu and select dark. That's it, now let's drop down the attribute VOP. Connect the pig head, then dive inside. Now I want to show you the align node. Let's create it. This operator computes a matrix representing the rotation. To align the geometry in the specified direction, we just need to multiply the position vector by the output matrix of this node. Before multiplying, I want to adjust the initial settings of the align node. Since the pig's face is directed along the positive z-axis, we will set the same direction for the first vector. The second vector is directed along the positive y. Now let's multiply the position by the output matrix. Look, we aligned the pig head along the positive y. Of course we can align any direction we like by changing this vector. Okay, let's move on. Now I want to align the pig head using some primitive. Let's create a sphere. We also need a transform node. Then connect the sphere to the second input. Let's move the sphere in front of the pig's nose. Something like this. Okay, now I'm going to import the sphere position. Connect the second geometry to it. Create a constant to specify a point number of 0. Now we can use the sphere's position as an alignment vector. Okay, let's jump at the object level, then tweak the sphere and see what we get. Here we go, the pig's head is always looking at the sphere. Let's move on. The align node is able to output a quaternion. Let's duplicate the align node. Then choose an angle axis from this menu. That's it, now the output is a quaternion. Let's check if the result will be the same. For that we need a rotate by quaternion node. Connect position to it. Then quaternion. The output vector goes to the P. Let's check out. As you can see, the result is absolutely the same. Okay, now we can remove the nodes associated with the quaternion. Then return the old connection. Okay, now I want to show you the problem that you will face when using this node in most cases. Look, now I'm pulling the sphere inside the XZ plane. As you can see, the pig's head follows the sphere without any flipping. Now let's move up a bit the sphere, then try again. Take a look, the pig's head is flipping. Okay, now I want to show you another node that you can use to avoid flipping, and in addition it gives us some extra control. The node is called look at. This operator computes a 3x3 rotation matrix to orient the z-axis along the vector to from under the transformation. If an up vector is specified, it will determine the roll. Now let's connect the sphere position to the first input. The output will replace the old connection. Great, now let's check what we have. As you can see, Unlike the align node, there is no flip because the lookat node has an up vector. Now let's create an extra sphere to control the up vector as well. Let's move it up. Then connect the third input. Let's duplicate the import point attribute node. Connect the third geometry to it. Okay, the second sphere is going to drive the up vector. That's it, let's check what we get. First, let's change the orientation of the pig's head. Now let's tweak the up vector. As you can see, the up vector gives us an additional control to rotate around the lookat vector, and there is no flip. Okay, let's reset all tweaks, then go ahead. The lookat node does not output quaternion like an align node, but if you want, this can be done through conversion by matrix 3 to quaternion. This operator converts a matrix 3, representing a rotation, to a quaternion representing the same rotation. Let's connect a rotation matrix to it, then create a rotate by quaternion node. Connect the position to it. Then connect the quaternion. The output to the P. Now let's check if the result is the same. As you can see, we have absolutely the same result. You can even do the opposite conversion from quaternion to rotation matrix. Okay, let's move on. For further work, we only need an align node, so let's get rid of the rest. Okay, now I'm going to manipulate each primitive of pig head geometry. Let's jump at the object level. We can also delete the second sphere, we no longer need it. Okay, now let's create a facet node. Turn on the unique points option, just to separate the primitives from each other. Okay, let's move on. Now let's create an import primitive attribute. This operator can fetch the primitive attribute from the specified geometry. Look, with this node I'm going to import the centroid position of each primitive. Connect to it the pig head geometry. Then we must give primitive numbers. Okay, now let's subtract the centroid position from the point position to send them all back to the origin. Here we go, they all are in the origin. Okay, now we need to do exactly the opposite, return them to their original position. Excellent, now we are able to manipulate each primitive around its centroid. Let's arrange the nodes so that there is no mess. Okay, now let's check what we have right now. As you can see, the sphere position is an alignment vector for all primitives. Let's reset the sphere tweaks and go on. Now I want to make each primitive look towards the sphere. For that we just need to subtract from the sphere position the primitive centroid positions. Okay, let's connect the difference vector to the align node. Let's check what it looks like. Here we go, each primitive looks towards the sphere. The only thing I want to change is to exclude the movement of primitives far from the sphere. Okay, let's create a distance node. We can maximize the network window. Now let's measure the distance between the sphere and each primitive. Visualize the distance attribute. Let's move the sphere closer to the pig head. Okay, now we can adjust the distance attribute. Let's fit the distance. Put a 10 for source max and 2 for source min. Okay, now let's create a mix node. Connect the alignment vector to it. Mixing will occur with a vector directed along Z. Connect to align node the mix output. Okay, let's slide the bias parameter and see what we have. Look, when bias is 1, the orientation of primitives is unchanged. And when bias is 0, each primitive looks towards the sphere. Now let's drive the bias by distance. That's it, as you noticed, the primitives that are farther from the sphere were left intact. Okay, now let's tweak the sphere and see how it looks in action. Excellent, let's move on. Delete the visualize node. Now I want to create a color based on the distance. Connect the distance to it. Instead of using this geometry VOP output, I suggest creating a new one. Connect the ramp to CD. Okay, now let's set up the color ramp. That's it, now let's tweak the sphere and see how it looks with colors. Here we go, we've created a cool effect using a few simple nodes. That's the beauty of the VOP network. Since our setup is completely procedural, we can replace the pig's head with any other geometry. Now let's replace the pig's head with a torus and make sure that everything works correctly. Put a 10 for uniform scale. Let's increase the rows and columns. Then replace the pig's head. Great, now let's check if it works as it should. As you can see, all works correctly. Now I propose to stop there and then do something new. Okay, let's get started. This time I want to show you how you can extract a transformation matrix from a moving object. Look, I've prepared this simple animation in advance, from which we're going to extract the transformation matrix and then use it to move another object. Excellent, let's create an attribute VOP. Connect the geometry to it, then dive inside. Our first step should be to create a local coordination system that is attached to this geometry and moves with it. Okay, let's display point numbers to help us build a coordination system. Create an import point attribute. Connect the geometry to it. I'm going to import the position of point 24. Okay, let's call this point 24. Now let's duplicate these two nodes. Rename it to point 10. Then specify point number 10. Let's make a copy again. Rename point 25. Then specify point number 25. That's all. Now we can build a coordination system based on these three positions. Let's create a subtract node. Then subtract point 24 from point 10. Okay, now we get a vector directed from point 24 to point 10. Let's normalize this vector, then export it as a y-axis. Specify the type as a vector, then call it y-axis. Let's give it a green color. Now copy this subtract node. Connect the point 25 to the first input just to get a vector directed from point 24 to point 25. Let's normalize again this vector. Then export it as an x-axis. Let's make it red. I will swap these two nodes just to have a correct order. Excellent, now we can generate the z-axis based on these two vectors. Let's create a cross-product node. Connect these two vectors to it. Then export it as a z-axis. Let's make it blue. Here we go, now we have a coordination system. Now let's organize these nodes, select all this, then create a subnet. That's it, now I want to visualize these three axes and see what it looks like. Let's right-click on this icon. Then click on the plus, select marker. Let's call it an x-axis. Specify as a vector. Select a point. Then choose an x-axis from here. Let's color it red. That's it, we visualized the x-axis. Now let's do the same for y and z-axis. Take a look, now we see all three axes. The only thing I want to change is to invert the z-axis. For that we just need to swap the cross-product inputs. Let's get to it and fix it. Select the cross product and press Ctrl-R. That's all, we reversed the z-axis. Okay, now we have a local coordination system, it means we can extract the transformation matrix relative to it. Let's disable the visualization of vectors. Then click on this to expand the network view. Then press P to bring up the parameters window. Okay, now let's extract the rotation matrix from this animated tube. For that we need a vector to matrix 3 node. This operator converts row vector values to a 3 by 3 matrix value. We must in turn connect these three vectors to it. Now let's export this rotation matrix. I will call it rotate matrix. The type must be matrix 3. Now we can try to rotate another geometry by using this rotation matrix. Let's check the newly created attribute. Here it is. Now let's create a box. Then create a one more attribute VOP. Connect the box to the first input. the animated geometry to the second input. Then dive inside. Now let's import the rotation matrix from an animated object. Connect the second geometry to it. The point number can be any point of tube because a rotate matrix attribute exists on each of them. Specify the type of attribute we are going to import, then enter the name of the attribute. That's it, we import the rotation matrix, now let's use it to rotate the box. We have to multiply the position vector by this matrix. Now let's check what we get. Here we go, the box perfectly repeats all the rotations of the animated tube. In order to repeat the movement of the tube, we have to extract a full transformation matrix. Okay, let's go on. Now I want to exclude rotation from animation using inverse rotation matrix. For that we need to multiply the position by the inverse rotation matrix. Now we need to invert the rotation matrix. This operator computes its inverse. Okay, let's check what we get. As you can see, we exclude the rotation, the tube only moves. Okay, let's move on, we can delete these two nodes. Now I want to extract the full transformation matrix. For that we need a vector 4 to matrix. This operator converts row vector values to a 4x4 matrix value. As you can see, this node takes only vector 4, but if you connect a regular vector to it, the Houdini will automatically convert it to vector 4. But still I'm going to convert. Let's create a vector to vector 4. Then convert the regular vector to vector 4 and connect to the first input. Okay, now let's convert the rest two axes. Then connect to the vector 4 inputs, in turn. That's it, we only need to set the fourth input, which should be a position vector. Let's create an import point attribute. Connect the geometry to it. Look, I'm going to import the position of point 24. Let's create a constant, then put a 24. Now we need convert the regular position vector to vector 4, then connect to the fourth input. For the position vector we have to make a 1 the fourth component. That's all, we have extracted a full transformation matrix. Now I'm going to export it, then use it to move the box. Let's call it a full transformation matrix. Specify the type. Great, now let's use this to drive a box. Duplicate the import point attribute. Enter the name. Then specify the type. Okay, now let's disconnect the rotation matrix, then connect the full transformation matrix. That's it, let's check what we get. As you can see, now the box repeats not only the rotation of the animation object, but also the movement. The box is attached to the point number 24. If we change the point number, then the attachment location also changes. Let's check out. That's it, the box sticks to the point from which we take the position. Now I want to show you how you can stop the animation and bring the geometry back to the origin using the full transformation matrix. For that we just need to multiply the position vector by the inverse transformation matrix. As you noticed, the point from which we take the position has moved to the origin. In this case it is point 24. Now let's display the point numbers and check. That's it. Now let's change the point number and see what happens. As you can see, the specified point goes to the origin, since the transformation matrix is built based on it. Now let's move the time slider and see what happened to the animation. As you noticed, the torus is not moving because the inverse transform matrix compensates for the existing animations. Okay, let's go on, we can delete these two nodes. Now I want to show you one more important thing related to this kind of manipulation. Let's increase the radius of this tube. Something like that. Delete the box, then create a torus. Let's scale down the torus, then reposition it. Something like that. Okay, now let's connect to the attribute VOP to move with the animated tube. Look, the torus has changed its original position, which is undesirable. Now I want to improve our setup and get rid of this unwanted shift. The reason for this shift is the offset of the point from the origin, on the basis of which the transformation matrix was built. It turns out if we change the point number, on the basis of which we extract the transformation matrix, then the offset will also change. Here we go, the reason for the offset is determined, now let's solve the problem. Okay, let's jump to the object level. Then connect the static tube to the second input. Let's make sure that the second input has no animation. As you can see, the tube is not moving. Let's dive into the attribute VOP. Now let's copy all this network. Then delete extra nodes which we don't need. Let's arrange this network a bit. Okay, now we need to specify the second geometry, which is a static tube. We also need to pick the same point for both geometries. Let's delete this one. Now let's rename the full transformation matrix of the static tube. I will call it offset from origin. Okay, let's use this matrix to get rid of the shift. Here is a newly created matrix. Excellent, let's jump inside the second attribute VOP. Delete the rotation matrix, we don't need it anymore. Let's duplicate this node, then import offset from origin attribute. Create one more multiply node. Then multiply the position vector by the inverse of this matrix. Here we go, the torus returned to its initial position, we compensated the shift. Now let's check if the torus is attached to the animated object. Here we go, the torus moves with the animated object. Look, now we can move the torus where we want, and it will be attached to the animation object. We can even change the point number from which we built the transformation matrix. Take a look, we have no shift. Okay, let's move on. The last thing I want to show you is how to exclude the translation and keep only rotation from the full transformation matrix. For this there is a special node called orient. This operator reorients a vector representing a direction by multiplying it by a 4x4 transform matrix. The translations associated with the 4x4 matrix will be ignored. Okay, now let's connect the position vector to it. Then multiply it by the transformation matrix. Connect the output vector to P. Now let's check what we got. As you can see, the torus doesn't follow the tube when we transform it. But as we start to rotate it will follow. Here we go, we keep the rotation but exclude the transformation. That's all, this concludes whole lesson. I hope it was useful for you. I did my best. See you in the next lesson.